Hey ChemStars, it's Ms. McCauley, and today we're going to be going over Chapter 2 Practice, pages 9, 10, and 11, which is all about error calculations and then accuracy and precision and measuring tools. Okay, so you saw some of this in your notes. We're going to talk about percent error. It's a way for scientists to express how far off a laboratory value is from the accepted value. So here are the formulas we need. Error is the experimental minus the actual, and then percent error is the accepted value minus the experimental over the accepted. Now, some of those words might be a little confusing, so let's kind of label these out. So experimental, that's what you measured in the lab. So anytime we see experimental, that's what you got in the lab. Now here, we use the words actual or accepted. That means the same thing. This is what it should be. So what it should be. So that the actual, what is the thing actually in real life? So remember that experimental is what you measured in the lab, and then actual or accepted is what it actually should be. We also have the absolute value right here, so this will always be a positive number. We can't have negative percentages. Okay, so let's do number one together. So here we have the experimental value, that's the lab, and then the accepted value is 1.30. Now, we can have a positive or negative error, so let's look at that. So it's experimental first, so it's going to be the lab value, 1.24 grams, minus the accepted, what it actually is, what it should be, so minus 1.30. Okay, and you can see there 30 minus 24, we have a negative 0.06. That negative sign is important because it's saying that we were too low. If it had been positive, we would have been too high. So my answer for the error is negative 0.06 grams. Now what about the percent error? Well, we've got to take this, which is the actual error, over what it should have been. So I'm going to skip writing that step out again because we just did the lab. Oops, sorry, it's backwards. Well, it doesn't really matter. It's the absolute value of the difference. We'll get the same answer either way. So that difference is either going to be 0.06 or negative 0.06 over the accepted, what it should have been, 1.30 times 100. So it doesn't matter because we have the absolute value, which way we took that difference. Okay, so 0.06 divided by 1.30. Now that number looks really small. We got to times by 100 to get a percent. So 4.6%. We haven't got the sig figs yet, so just trust me. We're going to say 4.62%. Next section, we're going to get there. And there are no units because it's actually going to be grams over grams. So those units cancel, and our percent error is 4.62%. Not too bad. Okay, now the next one. This one's a little tricky. On my calculator, I don't have easy to use scientific notation. So let's put these numbers in the standard form. Let's practice that. So we have to move the decimal 2 places, and we want to make it smaller. It's negative. So I'm going to go 1, 2. This is actually 0.0124 grams. This is the lab measurement. And then accepted, okay, we need to move 3 places to make it smaller. 1, 2, 3. 0.00998. Now I can plug it into my calculator nice and easy. Okay, and so let's make sure that we go the right direction, we get the right sign. It's the lab minus what it should have been. Okay. So the lab number is 0.0124 minus what it should have been, 0.00998. My difference is 0.00242. Let's make sure I got that right. 242 grams. Now that's a positive number. Okay, so we were actually a little high. So we were over. See how last time we were negative, we were too low in our measurement? This time we're too high. Okay, so the percent error, we're going to take the absolute value of that, 0.00242, and divide it by what it should have been, 0.00998 times 100. Now my units are grams and grams. That cancels out. So divide that by 0.00998 times 100. And we're going to get 24.2. 24.2%. So on this problem, the percent error is a lot bigger than the last one, even though the actual difference is very, very small because we were so far off from the accepted value. Let's make a note in case you got a little bit confused. So the error that we've been talking about is the experimental minus the actual. The percent error, this is essentially the same thing right here. This is the error. Okay, we took the absolute value, so it doesn't really matter the order, over the accepted. So when we have that error measurement, all we have to do is divide by the accepted and times by 100. Okay, let's see. We've got a couple more left on this page. Experimental value is 252. Accepted is 225. So let's take our 252 minus 225. Now, real quick, were we over or were we under? We were over. This should be a positive error. We were too high. And we get 27. So we were off by 27 milliliters. So what's my percent error? It's going to be the absolute value of the error over the accepted times 100, which is going to be 27 over 225. Now my units are mils and mils. That cancels. Times 100. So divide by 225 times 100. Now we've got a 12% error. No units because the milliliters canceled. Okay, let's see. One more on this page. Oops, too far. Okay, so now we've got experimental 22.2, accepted 22.4. Look at these real quick. We were low. We know our answer should be negative. We were too low on this one. Okay, so 22.2 minus 22.4, units are liters. We are negative 0.2 liters. So negative 0.2 liters. We were low. So percent. We're going to take that error, so 0.2, the absolute value of it, over the accepted, over 22.4 times 100. So divide by 22.4. Remember, it's the absolute value, so that negative sign doesn't matter. We are 0.89% off. Actually, we're going to go 893. 0.893%. Good. So if you have any questions, just make sure you go back to your notes, check the work, and let your teacher know. Okay, page 10. This is all on measurement. I'm going to go back to my old answer keys. These are the same pictures, I think. So the first part, you're just reading this metric ruler. Okay. Now remember what we learned in the notes. It's important to check the scale, make sure you understand what each line is. So right here, these are centimeters. So that's 1 centimeter, 2 centimeters, 3 centimeters. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 lines. So every line is 1/10 of a centimeter, or every line here is a millimeter. Okay. And to go from centimeters to millimeters, that's a metric conversion. We're going to move 1 time to the right. So it's going to be bigger. Okay. So we also remember, if we're looking at A, and it looks like it's right on the 0.5, we need to read one place and guess one more. So on this page, if I'm saying, oh, 0.5, that's what I'd say in math class. But I'm pretty sure it's right on the line. I can read the 0.5. I'm actually going to call this 0.50. Now to convert to millimeters, we can just count the line. We can read 1, 2, 3, 4, 5. Well, I'm sure it's on that line. It's 5.0. So on all these values, we want to make sure we're saying how accurate, how precise we are. So for B, I'm reading that as 3.3. I want to actually say it's 3.30 centimeters. And then in millimeters, if I count every single little line, it's on the 33rd line, 33.0. C, exactly 5.5. So I'm going to say I'm sure about that, 5.50. And that means that in millimeters, it's 55.0. D, it's exactly on 7, okay? So I'm going to say 7.0. Actually, I should say 7.00 because I can read it being on that line. Okay, so see how the tenths are marked? That means I should have a ones value, a tenths value I can read, and every single one of these, I'm guessing the hundredths. So I should say 7.00 to be specific here. Same thing for E. I think it's 8.3. I'm going to say 8.30. So 70.0 millimeters and 83.0. So see that specificity? That's important. Okay, let's go to the next section. Now this next section, you need to use a centimeter ruler. If you don't have one available at home, just kind of trust me off of this. Maybe you can find one on the internet. Ooh, your iPhone, I think, has a measurement tool built in. You can use that iPhone app. If it's not available to you, though, let's just take a look. So my centimeter ruler, I could read the ones and the tenths, and I guessed to the hundredths. Okay, so if you need to, pause the video here and take a look at all of my measurements. Okay, good. So, oh, that's the same thing. That's my old answer key. Where are we at here? Oops, let me see. We need to get the page with the, here we are. This got out of order. This is what we want to do next. This is your next page. Okay, so what is the volume on each of these graduated cylinders? Each one's in mil, but they have different scales. Remember from your video notes, we need to read the bottom of the meniscus. Meniscus. That is that curved line. So what is the meniscus? It's this curved line right here. So that's, well, pretend it was a curved line when I drew it. This line right here. Okay, now every graduated cylinder here might have different units, so we got to figure out that scale first. So here's 50, and here's 60. So this must be 55. So going from 50 to 55, 1, 2, 3, 4, 5. So every line here is 1 milliliter. That means I can read to the nearest whole millimeter. I should be guessing to the nearest tenth. So here's 55, 56, 57, 58, 59, 60. So this is 56. This is where the bottom of the meniscus is. So in that class, you say, yeah, 56 mils. But we're in science class. So since I'm sure it's on that line and I can read to the ones place value, I'm going to be specific and say it's 56.0. So remember, all of the digits you can read plus one that you're guessing. So let's try this next one. Uh-oh, different scale for sure. Here's 3, here's 4. Well, in between them, that must be 3.5. So let's count how many lines. 1, 2, 3, 4, 5. Every line here must be 0.1 milliliters. That's my new scale. So here's 4. Well, this must be 4.5. So 4.1, 4.2. Here's 4.3, and here's 4.4. So I'm right in between those. I can read to the tenths. That means I'm going to guess the hundredths. So what's in between those? 4.35 milliliters. Okay, let's see this scale over here. Different scale again, maybe. So 20, this must be 25. Here's 30. 1, 2, 3, 4, 5. Okay, so we have 1 milliliter here. So 21, 22. Here's 23. Here's 24. And it looks like we're a little over halfway, maybe. So you might want to say 23.5. I'd accept that. But could you also say 23.6? Sure. Could you say 23.7? Yeah. Could you say 23.8? I'm not sure. But as long as we're guessing that tenths value, any of those would be fine. Okay. And let's see, the last 3 on this page before we're done. So we got another different scale here. So here's 15, here's 20, 16, 17, 18, 19, 20. Okay, so every little line here is 1 milliliter. 15, here's 16, here's 17. So we know it's at least 16, and I have to guess the tenths value. So take a look at that real carefully. It's definitely over halfway between them. So maybe you're like, oh, it's 3/4. Let's say 16.75. No, you can't do that. Because in science class, we can only guess one more place value. So if you really want to say 16.75, you could say 16.7, you could say 16.8. Either one of those would be fine. This is a lie. You can't be that accurate and specific with your answer because we can only guess to the tenths place. You cannot make any judgment on the hundredths on this graduated cylinder. So be careful there. Okay, next one. Looks like we're going by ones again. Let's just double count, double check. 75, 80, 76. Yep, right here. Now this one, be careful. You would want to say 76, but I can read the tens and the ones. It's right on the line, so I've got to call that 76.0 milliliters. One last problem. Okay, so 40, 50, this must be 45, 46, 47, 48, 49, 50. Yep, right here we're going by 1 milliliters. So 46, 47. What should this answer be? Is it 47? it's 47.0. We can read the tens, we can read the ones place. This is the place value that we're guessing. Okay, so I hope that you're getting more confident in reading your metric rulers. Thanks, guys. I'll see you next time. Don't wait to be great. Bye.